So think about this. A single misclicked mouse button in a quiet, air-conditioned room could instantly turn $50 million of supercluster silicon into just, useless bricks.
Yeah, totally useless. It's a terrifying thought.
It really is. And today we are looking at the specific user interface designed to stop human beings from, well, basically destroying the internet. Welcome to the deep dive.
Thanks for having me. I'm excited to get into this one.
Me too. So our mission today is to unpack a document that, honestly, on the surface, sounds like the most standard IT reading imaginable.
Right, it doesn't sound like a thriller.
Exactly. We're looking at the April 2026 release of the Supermicro SuperCloud Composer, or SCC, Artifacts User Guide, release 3.12.0 version 1.0.
Which is quite a mouthful. And I know to anyone outside of, enterprise architecture, reading a 2026 software user guide might seem incredibly tedious.
Oh, for sure. You'd think it's just dry tech jargon.
But we are going to look at this through a totally different lens today, because this document is the literal blueprint for how modern digital infrastructure is governed. It dictates the exact interaction between, fallible human administrators and the raw firmware that keeps these massive multi-million-dollar superclusters alive.
Yeah, and before we get lost in the weeds here, we should definitely define our boundaries for you, the listener.
Good idea. Establish the scope.
Yeah, because the manual itself states very clearly that it does not cover the installation of the SCC application. There is an entirely separate guide for that.
Right, so we are completely ignoring the physical deployment today.
Exactly. We're focusing exclusively on the day-to-day governance of what the system categorizes as artifacts.
Which is a really interesting word choice, by the way. Artifacts.
It really is. So we are going to examine the rules of the user interface, the management of the network switches, the compute trays, and the power shelves.
So basically, we're examining the nervous system, the brain, and the cardiovascular system of a massive data center.
Yeah.
And it's all managed through this sterile glass screen.
And, the disconnect between the physical reality of a data center, the noise, the heat, and the virtual reality of this interface is jarring.
Oh, absolutely. It's a totally different world.
But before administrators even allowed to touch the virtual controls of this machinery, they are confronted with the rules of the house.
The legalese.
The legalese. I spent a long time reading the copyright and preface section, and I gotta say, the legal disclaimers are incredibly dramatic.
They really don't hold back.
No, they don't. The manual states, literally in all caps, that the software is provided strictly ASIS.
I say this, yeah.
Supermicro explicitly disclaims all warranties of correctness, accuracy, or reliability. If something breaks, the user assumes the entire cost of all necessary service, repair, or correction.
I mean, you really have to look at the economic reality behind that legal shield, right?
What do you mean?
Well, hardware manufacturers cap their liability at the price of the hardware, and they do that because the secondary operational revenue tied to a supercluster is astronomically high.
Oh, right. Because of what the cluster is actually doing.
Exactly. Imagine if a software glitch, or even just an administrative error, takes down a cluster that handles real-time financial trading algorithms.
Oh, wow, yeah. That's millions of dollars a second.
Or global logistics routing. The lost revenue per minute in those scenarios could eclipse the physical costs of the hardware in, an hour.
That puts so much pressure on the administrators. And the manual includes this very specific jurisdictional lock to reinforce that liability cap.
Right, the Santa Clara Clause.
Yeah. It mandates that any disputes must be governed by the laws of Santa Clara County, California.
Which is classic Silicon Valley legal maneuvering.
For sure. And it clearly states total liability will never exceed the price paid for the hardware product. It really forces the buyer to acknowledge that the manufacturer is just providing a management tool.
Right. The tool is theirs, but the risk is yours.
Exactly. The enterprise assumes the existential risk of actually wielding it.
And that intense legal framework directly informs the user interface design philosophy. I mean, it has to.
How so?
Because the UI cannot afford ambiguity. It must be completely rigid. When the stakes are that high, you can't have a playful or loose interface.
I totally noticed that rigidity right away when I was looking at the common features in the Artifacts module.
The icons, right?
Yeah, the manual outlines this very specific set of icons in the object list. So you have the upload icon, which is represented by an up arrow.
Very standard.
Edit is a pencil. Delete is a trash can.
Again, standard.
Reload is circular arrows. Display is an eye. and search is a magnifying glass.
And the reason for that is the iconography is universally recognizable. It drastically lowers the cognitive barrier to entry.
But this is where it gets interesting. The manual mandates a strict behavioral lock on those icons.
Right, they aren't just always available.
No, not at all. If the switch firmware list is empty, for instance, the system does not simply display a blank screen and allow the user to click around aimlessly.
Which a lot of consumer software actually does.
Right. But here, it actively disables the upload, edit, and delete icons. They're completely grayed out.
Locked down.
And if you hover your mouse over them, the system triggers this little toast notification that pops up and reads, "No resource found."
Ah, yes.
I've actually started referring to it in my notes as the toast of denial.
I love that. The toast of denial. But that is a prime example of defensive UI design.
Defensive UI, I like that term. Break that down for me.
Well, put yourself in a high-stress scenario. Imagine you're an administrator attempting to restore a degraded cluster at, 3 in the morning.
I'd be sweating bullets.
But you are stressed, you are tired, the system cannot allow you to execute commands on non-existent targets.
Because that would just make things worse.
Exactly. Ghost actions create log errors. Those log errors trigger secondary alerts, which then compound the cognitive load on the administrator who is already panicking.
Oh, I see. It's like a snowball effect of errors.
By disabling the icons entirely, the UI forces the human brain to synchronize with the true state of the machine before an erroneous input can even be attempted.
So it's protecting the user from their own exhaustion.
Yes. It's saving you from yourself.
That makes total sense. And, the search functionality seems to apply that exact same defensive philosophy.
Oh, the search is fascinating. It's so strict.
Extremely strict. When you click the magnifying glass, you get a drop-down of specific search fields, like file name, size, description, SKU, manufacturer.
They're very standard fields.
Right. But the manual explicitly dictates that if you enter criteria into multiple fields, the system applies a strict A&D condition.
Meaning it has to match every single thing you type.
Exactly. So if you search for an Arista manufacturer AD, a size of 1.038 gigabytes, the result must match both parameters flawlessly.
And this is such a departure from what we are used to. I mean, consumer technology has totally trained us to expect fuzzy logic, right?
Yeah, exactly. We expect search engines to guess our intent, to give us those little, did you mean this, alternatives when we make a typo?
Right, but the SuperCloud Composer rejects that entire concept.
Why is that? Why not be a little helpful?
Because fuzzy logic in an enterprise firmware search is a catastrophic risk.
Really? Just from a search?
Think about it. If a system tries to guess what operating system a core network switch needs, and it guesses wrong based on a typo.
Oh, wow.
Right, the deployment will fail. Or worse, it might deploy a conflicting version that completely destabilizes the routing tables for the whole cluster.
That is terrifying.
It is. The machine cannot guess. It must know.
And furthermore, the manual reveals this really critical layer of filtration in the search. The search values displayed are governed by the security restrictions of the logged-in user.
Yes, role-based access control.
That totally reframes how I look at organizational hierarchies. I mean, the implication here is that the UI is literally enforcing the HR chart at a silicon level.
That's a great way to put it.
Like a junior network technician running a search will only see Ethernet switch firmware, right?
Correct. They only see what they are cleared to see.
But a senior architect running the exact same search, typing the exact same letters, might see the primary compute bundles.
Exactly. The software dynamically reshapes its reality based on the security clearance of the human looking at the screen.
That is wild to think about. Two people looking at the same screen, running the same search, getting totally different results based on their job title.
Because the UI is not just filtering data, it is actively mitigating insider threat and accidental overreach.
It's building walls inside the search engine.
Precisely. So we have established the boundaries of the cockpit here, right?
Yeah, we got the legal shields, the defensive UI, the strict search parameters.
So maybe we should look at the first major component managed by this module, the stuff you're actually searching for.
Yeah, let's move into the switch firmwares. Because we've built this flawless, mathematically verified highway for the data to travel on, right?
That's the network switch.
And the navigation path in the manual to get there is, again, very rigid. You go to SuperCloud Composer, then Artifacts, then switch firmware, and finally Ethernet technology.
A very deliberate path.
And once you're there, the UI presents a capacity bar. It shows free, used, and total storage.
keeping you aware of your limits.
Right. And underneath that, we get the anatomy of a switch firmware entry. And this is where I want to spend a minute because the columns are super specific.
What are they?
You've got checkboxes, file name, state, SKU, manufacturer, MD5 checksum, size, description, created time, and owner.
Okay, let's examine the data prioritized in those columns, because order matters.
It does. The manual provides this reference file to look at. It's called qa.test.suy.
Okay, standard test file.
The state is available. The SUU is SSE3648B, manufactured by Supermicro.
Makes sense.
But then, prominently displayed as a primary column, right next to all this human-readable stuff, is the MD5 checksum.
Oh, yes, the checksum.
And I have to admit, I had some confusion here. Or at least, I want to push back on this UX choice for a second.
Okay, pushback. What's the issue?
To a human, file name, manufacturer, size, those are semantically useful. I understand what they mean.
Right.
But an MD5 checksum is just this massive, seemingly random alphanumeric string. It's gibberish to a person.
It looks like gibberish, yes.
So why is a background cryptographic detail taking up prime real estate on a visual dashboard meant for human beings?
Well, you might think it is a background detail if you are used to normal consumer software. But in enterprise architecture, it is the absolute foundation of trust.
Really, the most important thing.
That alphanumeric string is the most critical piece of data on the entire screen.
More critical than ensuring the SKU matches the hardware. If the SKU is wrong, it won't work right.
True, but think about it this way. The CU label is just human enter metadata. Someone type that in.
Okay, yeah.
The MD5 checksum is mathematical proof of purity.
Proof of purity. Okay, explain that.
Consider the life cycle of a massive switch operating system. Some of these .swi files exceed a gigabyte in size.
That's a lot of data for a switch.
It is. And when an administrator downloads that file from the manufacturer, it doesn't just instantly appear. It travels across wide area networks, through various routing hops, submarine cables, server farms.
Right, it's bouncing all over the globe before it gets to the repository.
Exactly. And it is finally stored in the SuperCloud Composer repository. Now, during that journey, things can go wrong.
You were talking about bit rot.
Bit rot, degraded hardware in transit, or even just cosmic ray interference.
Wait, cosmic rays?
Seriously. A cosmic ray can literally strike a memory module and flip a single transistor state from a 0 to a 1.
That sounds like science fiction.
It happens. And if even 1 0 or 1 out of billions is flipped during that transit, the file is corrupted.
Wow, just one bit.
Just one. And if you deploy that corrupted .swi file to a top-of-rack switch,
What happened?
the switch will fail its boot sequence. It will completely brick. It will not turn on.
Oh, man.
And suddenly, you don't just have a broken switch, you have a cascading network failure across your multi-million-dollar cluster.
All because of one flipped bit.
Exactly. So how do you prevent this? The manufacturer publishes the official MD5 checksum for the pure, uncorrupted file.
Okay, so they give you the mathematical answer key.
Yes. When the file is uploaded to the SEC, the system calculates its own checksum based on the payload it actually received.
Oh, I see. So by displaying it prominently in the UI.
The system is forcing the administrator to visually verify that the two strings match perfectly before they even think about executing a deployment.
That is wild. It is the cryptographic equivalent of checking the tamper seal on a bottle of medicine.
Or a highly volatile chemical. You do not open the bottle if the seal is broken.
That fundamentally changes how I view the upload protocol described in the manual.
How so?
Well, when you click the upload icon, this window appears with a blue reminder box. It says strictly, reminder, only. Support file extension is SWI.
Okay, keeping you on track.
But below that, the user must manually select the manufacturer from a dropdown. They have to manually select the SKU, and they had to manually type in a description.
Notice the boundary of automation there.
Exactly. The system is orchestrating multi-million-dollar superclusters, right?
Yeah.
It's calculating these insane cryptographic hashes on the fly. But it refuses to auto-detect the SKU, or the manufacturer, from the file payload itself. It actively forces the human to manually input that metadata.
Because it forces semantic categorization onto the human.
Right. It's like the system is saying, I can do the math, but you need to tell me what this actually is.
The machine handles the heavy lifting of storage, deployment, and that complex cryptographic verification. But the machine demands that the human declare the intent of the file.
It completely prevents operational laziness.
Oh, 100%.
Because if the system auto-detected everything, administrators would just blindly upload hundreds of files, trusting the machine's parsing engine.
And eventually the machine would make a mistake.
Exactly. By forcing manual drop-down selections, the UI insists that the human remains the final arbiter of truth.
A superhighway is completely useless if there is no brain at the destination deciding what the traffic actually means.
That's a great analogy. And speaking of brains, that brings us down the data browser tree into the compute trays.
The actual thinking machines of the cluster.
Right. The navigation moves from artifacts to supercluster firmware, and then compute tray. And the manual divides this section into two distinct parts.
Okay, what's the first part?
The first is the firmware bundle.
Ah, the primary payload for the computational hardware.
Yeah, and the manual provides a highly specific file name for this as an example. It's called, wait, let me read it. NVFW GB200P497501124123121 custom prod sign.fwpkg.
That is a very serious file name.
Very serious. It is 119.7 megabytes with the description reading GB200FW bundle.
Okay, 119 megabytes.
And when I analyze that .fw package extension, I don't just see a single file. I see a comprehensive survival kit for the whole tray.
Survival kit is a brilliant way to put it.
Well, because a compute tray is not just a single processor, right? It contains memory controllers, PCIe bridges, power regulators, cooling sensors.
So many independent systems.
And updating those components individually via separate streams would be a nightmare.
Oh, it would introduce version mismatch vulnerabilities that could literally tear a cluster apart logically.
So the .fw package bundle is this single mathematically signed package that contains all the distinct microcodes needed for the primary compute unit to function in perfect harmony.
Right. The orchestration system must unpack this 119 megabyte file, verify its internal signatures.
Which we know is super important.
Right. And then it has to stage the deployment to the PCIe bridges and memory controllers without bricking the active session.
But look at the scale shift here. This really surprised me.
What do you mean?
When we discussed the switch firmware earlier, the capacity was measured in gigabytes.
Right. Over a gigabyte.
Here, the compute tray firmware bundle list is measuring in megabytes. The massive GB200 bundle, the brain of this whole operation, is only 119.7 megabytes.
I see why that's surprising. You'd expect it to be bigger.
I totally would. I mean, I would assume the brain of an AI supercluster would require significantly more software than just a network switch routing traffic.
It's a common assumption, but it reveals the fundamental distinction between high-level operating systems and low-level machine code.
Okay, break that down.
A network switch operating system has to manage routing protocols, access control lists, monitoring daemons, user interfaces. It is effectively a full-blown Linux environment running on that switch.
Just so it's bloated, kind of.
Well, it's comprehensive, but the compute bundle, that is much closer to the metal.
Closer to the metal.
Yeah, it is highly optimized, incredibly dense machine code. Its sole purpose is to initialize the physical silicon and then hand off control to an overlying hypervisor or an external operating system.
Oh, so it just wakes the hardware up and says, okay, I'm ready for instructions.
Exactly. It does not waste a single kilobyte of space on graphical interfaces or fluff. In this environment, its efficiency is its security.
That makes a lot of sense.
Yeah.
But, you know, the fundamental flaw of any primary processor is that if the firmware update fails, if it bricks him, the processor cannot recover itself.
It's dead in the water.
Right. Which brings us to the second part of the compute tray management in the manual, the BMC.
Ah, the baseboard management controller, the ultimate safety net.
Yes. The files in the BMC section use a .bin extension.
.bin. Binary.
And the manual cites another incredibly long file name, NVOBMCGB 2NG NVL36AST Civer701 MSS 2600 MS 27 207310002.02.040 EMST. That
It's
pin.
right off the tongue.
Doesn't it? And that file is weighing in at 67.1 megabytes.
Okay, pretty small.
But think about the context here. We're using a massively sophisticated UI-driven orchestration platform to deploy a 67 megabyte file to a tiny little monitoring chip.
It feels like overkill.
It totally feels like a Russian nesting doll of software governance.
It does, but you have to understand what it's for. It is out-of-band management. We really need to define what a lights-out scenario physically entails in a modern data center.
Okay, paint me a picture. What does lights out mean?
So if the main processor of a compute tray catastrophically fails during one of those .fw package updates,
Right, the 119 megabyte update failed.
yes, the primary primary network ports go completely dark, the hypervisor crashes, the machine is effectively a doorstop.
Total failure.
Now, in a traditional consumer setup, if your PC does that, someone would just have to walk over to the machine, physically pull the power cable out, and plug it back in.
Which you can't do here.
Exactly. Which is impossible if the hardware is distributed across a dark site data center, meaning there are literally no humans there 1,000 miles away from where you were sitting.
You can't just walk over to rack number
You
4.
can't.
Oh.
So the BMC operates on an entirely separate physical and logical plane from the main computer.
It's independent.
Totally independent. It is a system on a chip with its own dedicated power path and its own dedicated network interface that completely bypasses the primary switch fabric.
Oh, wow. So it's basically a mini computer strapped to the side of the big computer.
Yes. That 67.1 megabyte .bin file is a localized, stripped-down operating system that remains awake even when the main processor is effectively dead.
So even if the main brain is fried, the BMC is sitting there blinking, waiting for commands.
Exactly. Through the BMC, an administrator can connect, read the hardware temperature sensors, access a remote terminal to see the actual boot failure logs, and literally force a physical power cycle of the main processor tray
From 1,000 miles away.
without anyone ever touching a cable.
That is incredible. So if you corrupt the main .fw package deployment, the BMC is your safety net.
You can use it to reflash the primary brain and save the day.
What? What if you corrupt the .bin file deployment for the BMC itself?
Well, if you do that, you have completely severed your out-of-band access.
And then what?
Then you're deploying a technician with a crash cart, paying for a flight or a long drive, to physically walk into that dark site, open the rack, and rip the server out by hand.
Oh man, the dreaded physical intervention.
It's the absolute last resort, which perfectly explains why the SuperCloud Composer treats that tiny 67 megabyte BMC firmware with the exact same UI rigor, manual categorization, and MD5 verification as the massive primary bundles.
Because if the BMC fails, you have no more safety nets.
None. You are flying blind.
Wow. Okay, so we have a secure highway for the network. We have compute brains with these independent out-of-band management systems. But none of this architecture, not a single bit of it, survives a millisecond without a perfectly regulated heartbeat.
Electricity. The infrastructure requires power.
Exactly. And that brings us to the power shelf section of the manual.
The cardiovascular system, like we said earlier.
Right, and the data browser separates the power shelf into two distinct components, the PSU and the PMC.
Now, this separation perfectly mirrors the physical redundancy and logical division we literally just analyzed in the compute trace.
Oh, so.
Well, the PSU, the power supply unit that handles the raw transformation of energy.
Right, taking power from the grid.
Right. We don't need to discuss basic AC to DC conversion, but the sheer volume of power these units draw in a supercluster requires massive, heavy physical blocks of hardware.
They are the heavy lifters of the rack.
Exactly. But raw power is incredibly dangerous if it isn't intelligently regulated.
Which is where the PMC comes in.
Yes, the power management controller.
Okay, so what does the PMC actually do?
The PMC firmware is the brains of the power. It is responsible for load balancing across multiple redundant PSUs, monitoring phase synchronization, and managing thermal thresholds based on dynamic power draw.
So it's making sure the power doesn't just flood the system and melt everything.
Exactly. So the software architecture of the SuperCloud Composer is perfectly mirroring the physical division of labor down in the rack.
You have an artifact for the raw delivery of power and a completely separate artifact for the intelligent regulation of that delivery.
And manipulating the artifacts that govern that power delivery is arguably the most precarious action an administrator can take in the entire UI.
Because if you mess up the power, everything dies instantly. No graceful shutdown, just darkness.
Yes.
This is exactly where I want to deeply analyze the edit and delete protocols outlined in the manual.
Oh, the deletion process. It's intense.
It is, because deleting the wrong PMC firmware file literally removes the intelligence from the power shelf, potentially taking down the entire rack. And the UI for deletion is engineered to create this intense cognitive friction.
Cognitive friction. Walk us through the exact mechanism of deletion, step by step.
Okay, so imagine an administrator wants to delete an obsolete firmware file just to reclaim some space in the repository.
Routine maintenance.
Right. They cannot simply highlight a row and press the delete key on their keyboard. The UI ignores that.
Good. Too easy to hit by mistake.
Exactly. First, they must move their cursor and explicitly select a tiny checkbox on the far left of the screen corresponding to the specific firmware file name.
Okay, so that is the initial state change. You are targeting the file.
Second, they must physically travel across the screen with their mouse to the function group bar and click the trash can icon.
The execution command.
But the file's not deleted yet.
The system stops them.
Right. The system interrupts the workflow by summoning a modal pop-up window directly in the center of the screen titled Delete Firmware File.
It breaks their momentum.
Yes. And inside that window, the system confronts the user with a very specific question. It asks, would you like to delete firmware file below? And then it prints the exact name of the file in bright blue text. For instance, EOS 4.26.3 MCA.
That right there is the cognitive verification step.
And finally, the user must actively click a distinct blue button labeled Yes. Only then, after all of that, does the system actually attempt the deletion, resulting in a final toast notification of success or fail.
It's a digital safety catch.
Like on a weapon.
Yes, but specifically a dual action safety catch. You have to pull the slider back by checking the box before the trigger the trash can even engages.
Ah, I see.
It is forcing cognitive friction into muscle memory.
And I was thinking about alert fatigue when I read this.
Oh, alert fatigue is a massive issue in enterprise IT.
Right, because administrators are bombarded with thousands of dialog boxes, warnings, and alerts a week.
Every single day.
And they develop this really dangerous muscle memory where they instinctively just click OK or Yes without even reading the prompt just to clear the screen so they can do their job.
The UI designers at the SEC are clearly acutely aware of that psychological vulnerability.
Because they made it a four-step process.
Exactly. By requiring 4 distinct physical and cognitive actions, checking a box, moving the mouse to a specific icon, reading a targeted prompt containing the specific payload name in a different color, and confirming with a final button.
The system is attempting to literally shock the human brain out of autopilot.
It forces the administrator to acknowledge the severity of the action before the machine actually complies.
It's just so fascinating to see human psychology baked into something as dry as a firmware management manual.
It really is.
Well, we have spent quite a while dissecting a single software manual from 2026.
And we covered a lot of ground.
We did. We started with the liability caps that established the existential financial stakes of operating this equipment.
The Santa Clara Clause.
Right. Then we analyzed how disabled icons, the toast of denial and strict search parameters, build this defensive perimeter around human input.
Preventing those 3 a.m. mistakes.
We looked at how MD5 checksums protect network switches from things like bit rot and cosmic rays, and how .fw package files orchestrate the primary hardware, while the .bin files safeguard the out-of-band access.
The safety net for the safety net.
Exactly. And finally, we saw how the interface forces semantic categorization to prevent automated laziness, and how those dual-action deletion protocols attempt to break the dangerous muscle memory of alert fatigue.
It all paints a very clear picture of modern data center management.
It does. And the overarching theme here is that as the hardware inside a supercluster becomes more incomprehensibly chaotic and powerful, the interface required to govern it must become increasingly rigid, predictable, and heavily guarded.
The manual ultimately proves that true power in enterprise technology is not just the physical silicon, it's not just the chips.
No. What is it then?
The true power lies in the constraints of the user interface that allow a fallible human being to interact with that silicon without instantly destroying it.
That is such a profound way to look at it. And, I want to leave you, the listener, with a final thought on that exact dynamic.
Go for it.
The Supermicro SCC manual meticulously documents the exact clicks, the specific dropdowns, and the required confirmations needed to upload and deploy the code that keeps our entire global data infrastructure running.
It maps out the perfect interaction.
Yes, it maps out the perfect interaction between human and machine. But what this manual doesn't detail, and honestly, what no technical specification or UI design can ever truly solve, is what happens in the physical world when an administrator, maybe at the end of a chaotic 14-hour shift, overcomes all of that engineered cognitive friction.
When they push through the safety catches.
Exactly. What happens when they actively select the wrong checkbox, read the blue prompt, and just hit that final yes button anyway?
Because humans are human.
Right. We have perfected the digital interface for controlling the machine. But how do we ever perfect the human clicking the mouse?